This is real music. Dark, brooding, important, groundbreaking. Check out the lyrics. Darkness.
Could not resist that song, even though darkness is about the opposite of what we're talking about today. We're talking about light and how it's a particle, this time in quantum mechanics. Quantum mechanics is probably our strangest topic all year, so therefore I broke out my strangest hat. If you recognize who this is, write it in your comments for this video. But quantum mechanics is basically the physics of the small. This over here, it's how we deal with things that are really, really small. It turns out that it's very, very different than we do with our regular physics. It has to do with the word quantum. The word quantum means things coming in bundles, and it turns out that when things get really, really small, they don't come in every different possibility. They only come in bundles of a certain amount. The other thing that quantum mechanics is a lot about is about talking about light and how even though it's a wave, like we talked about last chapter with interference and diffraction, it's also a particle. So we'll talk a lot about light being a particle for this particular unit. Ugh, this thing is getting to be a little much for me, so I'm going to push it back a bit. Yeah, this is kind of nice too as a hat. This particular unit has a lot to do with the classical model breaking down. And so a lot of different places they tried to apply the classical model to small things, and it didn't give them the right answer. So this first picture is what's called black body radiation, right there. Black body radiation is the kind of light you get when you heat things up. According to our classical model of how light should work, we should get this blue line right here, that as our frequency went up, our energy density should go up as a nice smooth curve, probably an x squared curve. But it turns out that when they actually did the experiment, they got this pink curve instead. And that was a problem because that's not what they were expecting. And not getting what you expect is a lot of what this quantum stuff is about. It turns out somebody named Planck decided to try to model this a lot of the same way they did in calculus. Remember in calculus, if those of you are in calculus, if you're not in calculus, you just have to bear with me a bit. They put a variable in, they made it get smaller and smaller and smaller and smaller, wanted to get to zero, and then they got how to get the area underneath the curve. But Planck tried to do that with this graph, and the thing that he made smaller and smaller and smaller would never go away. And it turns out that it went to a certain value, which they gave his name. Well, he finally found the equation that would match up with that graph that he got there. The constant that he got was a really small number, 6.625 times 10 to the negative 34th joules times seconds. And it turns out that that is a fundamental constant of our universe. I think that that's one of the reasons why our universe is the way it is, because of that particular number. Planck wanted the number to go away, though, and so he never really believed his own results, even though they got him famous and they got his name on a constant, and if he had had a physics teacher, he could have gotten lots of brownie points. The main application of Planck's constant is to the energy of light. And it turns out the energy of light is dependent upon its frequency. The higher the frequency, the higher the energy. That's why high frequency light like blue has more energy than low frequency that's red. This right here is the equation that is the energy of a photon. And a photon is what we call the particle of light when we're talking about light as a particle. It's what's called quantized. Remember, quantized was things that come in particular bundles. The bundle that light is quantized in is Planck's constant. That's how it's bundled. It has to be some multiple of Planck's constant. It can't be anything else. And because it comes in those little bundles, that's why this is quantum physics. Here's two other versions of our quantized energy formula. If we plug velocity equals frequency times wavelength into our equation, we get this one right here, energy equals hc over wavelength. And we use that one a lot when we're doing problems, sometimes hf, but a lot of times this one. And then we can combine it with E equals mc squared to get E equals the momentum times the speed of light also. So we can use any of those to find the energy of individual photon for the purposes of quantum energy. Pretty straightforward, simple equation. Because we're dealing with really, really small amounts of energy, though, sometimes we don't want to use joules for our equations, or really, we want to use them for the equations. But sometimes we don't want to say that a photon has really, really small number of joules, so we do it in electron volts. An electron volt is 1.6 times 10 to the negative 19th joules, very, very small amount, and so it's for small things. And so a problem will give us the energy in 3.5 electron volts. But when we plug it into an equation, we always want it to be back in joules. So we have to use this conversion factor to change our 3.5 into joules, and then plug those joules into E equals HF to find the frequency of what we don't know. So we use that conversion factor a lot when we're dealing with small amounts of energy. Since we're dealing with light, we also know the speed that it goes at is a constant, 3 times 10 to the 8th, so we can find that wavelength of light from our frequency. And so this is a little quick problem about what color would this photon be. And so, we put that frequency in, does V, velocity equals frequency times wavelength. We find the wavelength, 344. We know the visible spectrum is from 400 to 700 nanometers, and since that's below that, that would be ultraviolet over here somewhere. Yeah. So you need to generally know the visible spectrum, and you need to know that you use velocity equals frequency times wavelength. So now we get to the second failure of classical mechanics. It turns out that we knew that incoming photons can hit a metal and they can create electrons going out. And if light was a wave, if we have a certain amplitude of light and we put a higher amplitude, that should increase the energy, because waves, if they have a higher amplitude, have a higher energy. And so therefore we should get higher energy electrons coming off, and it turns out that we didn't get that. We got more instead of a higher energy, and so this photoelectric effect was not explained well by the wave nature of light, and so therefore it took Planck coming along and saying, okay, well, maybe light's a particle for us to really understand this. But because Planck never really believed his own formula, he wanted to get rid of that H, he wasn't the one that got credit for this particular thing. He didn't find out how to explain the photoelectric effect. Einstein did. See Einstein? He's back there over my head. There he is. Hi, Einstein. This is what Einstein actually got his Nobel Prize for. He didn't get it for E equals mc squared, that really famous formula we're going to do this chapter. It was because he explained the photoelectric effect. And it was because they didn't really believe that E equals mc squared thing for a while. And they were pretty sure that this was true. These are the things that could not be explained by classical mechanics in that photoelectric effect thing. It was starting as soon as it hit, and that wouldn't have happened with classical. Why does certain frequencies work and other ones don't? Red won't, blue does. And why do we get more current instead of higher energy current when we have brighter light? And why does the energy depend on, what is it that it depends on? And Einstein said that all of this was due to the fact that light was a particle and not a wave. And he designed an experiment that would prove that. Now, Einstein didn't do experiments. He said, someone go off and do that for me, and they did. But he got famous even though he wasn't the one that ever did the experiment. But here comes the experiment. So this is a simplified version of the photoelectric effect experiment. We have up here a vacuum tube right there. And we need a vacuum in there because we don't want the electrons hitting anything when they come off. We have a light coming in. In this case we have blue light. It hits an emitter plate. And it gives off electrons. Some of those electrons will go all the way across to the other side, the collector plate. And because now we have a negative there and we're missing some here, we have positive there, that creates a potential difference and we get some current flow around the circuit. And if we put an ammeter there, we can measure how much current there is from that. And that's great. So that's how we knew that there were electrons going across because of that. That's not actually the experiment though. Here comes the experiment. What Einstein did was he put a battery over here and said if we put a battery right there, we can put enough potential there to stop the electrons from making it all the way across. And when we have a lower potential, then it won't stop them and they'll get all the way across. We'll be able to measure a current. And so what we do is we slowly raise this potential until no electrons get across, and then we can use that because we know that the energy equals QV, and so we can use that to find out with the stopping potential over here and the charge being the charge of an electron, we can know how much energy the most energetic electrons that are popping off of there have by figuring out how much potential it takes to stop them. Essentially, put some potential across that, figure out how much energy stops them. That's the amount of energy that the biggest, fastest electron that was going across would have had. When you do this and you find out what the stopping potential is for different frequency of light, you can pretty quickly see that there's a place where the frequency no longer has enough energy to get those electrons to pop off of there. And it turns out the reason why blue light will pop them off more is because blue light has more energy. That HF thing that Planck figured out but didn't believe himself, Einstein believed it. And so he said if you do this experiment, you'll get a nice graph that shows frequency and stopping potential, and from that you can find out a bunch of things about whatever substance you have. So Einstein's theory boiled down to this nice equation here. He said that the maximum kinetic energy that an electron is going to have as it's popped off from photoelectric effect is going to be HF, which Planck found out was the energy of an electron, minus a phi. That phi is called the work function, and it's how much work, basically how much a metal wants to keep its electrons. And some metals have a high work function. They want to keep the electrons a lot. Some metals don't really care too much about the electrons. They have a low work function. But the energy that the electron will have coming off is the total energy of the photon, which gives up all of its energy, minus however much it takes to get away. And because he sets up his experiment the right way, that's going to equal QV, or EV sub S, and he can use that to make a nice graph to analyze his data, just like we always do in physics. We like to analyze our data. So here's our graph. It's got stopping potential on the y-axis and frequency on the x-axis. Therefore, as our frequency is going up, it takes more stopping potential to stop them. In other words, our electrons are going to have more energy coming off as we have more frequency. And because Kmax equals HF minus phi, and it also equals EV sub S, we can combine those two equations and solve for V sub S to put it into y equals mx plus b, and then m is going to be our slope, which is Planck's constant over the charge of an electron. And so that's how we actually found, that's one way we can find Planck's constant easily, and they do that a lot in the AP test, is they'll give you this graph and ask you to find h. We also could find the work function if we extended this back and found b. We know that b has to equal phi over e, and that's right there. And at the cutoff frequency, the point right here where no electrons are pushed off of there, we know at that point that Kmax is 0, and if 0 equals HF minus phi, we can find that the cutoff frequency is phi over h, or if we want to find phi, we could say that the phi is the cutoff frequency, threshold frequency, times h. So you can find a lot of stuff from this graph, and they give you this graph a lot. Realize also they could sometimes give you instead the k versus frequency. That's even easier because then my slope is going to be Planck's constant and my intercept will be phi itself. But usually they do this one since that's the thing that you actually find is the cutoff potential. I mean, sorry, the stopping potential. Notice also that on this graph, the graph goes down to the cutoff frequency, then goes straight over. There's no stopping potential for anything lower than that because no electrons go off. And so, you know, the graph goes this way, then that. It doesn't have anything down there. So you'd have to extend it to find the B. And a lot of times you have to know that it comes up to a certain point and find where these two things, this one and this one, meet to find out the cutoff threshold frequency. Today's snack is sushi. I don't want to spend too much time on it because this one's going pretty long already, but you should get some sushi. If you've never tried raw fish and rice, it's one of my faves of all time. You should get some very soon and eat it. And another thing about light is if it's going to be a particle, it should have some kind of a momentum. Even though we sometimes think of photons as a massless particle, it still has momentum because we know that energy equals HF and PC, and so we can solve for the momentum, HF divided by C, and then we can plug in the velocity equals frequency times wavelength and get that the momentum is h divided by the wavelength. And Compton was the one that did that, and he set up an experiment to test that, and it worked. Here's what it looks like. Compton shot a lot of photons, at some electrons that were stationary. And when they hit the electrons, if it was a wave, it should go straight through them and should not have any effect on them at all because, waves can travel through things and when it comes out the other side, it should be the same, the whole superposition thing. But it turns out what happened was that the photon would hit the electron, they both go scattered off. Scattering means they go in two different directions, and because of that, it changed the momentum of the photon, which would change its wavelength, and so it changed the color of light when you would shoot it at some electrons, which shouldn't happen if it was a wave, but since it acts like a particle in this particular case, showing that it has some momentum because only a change in momentum would change that wavelength. And so Compton scattering is basically shown as a proof that light is a particle as well as the wave things we know, and the wave things are proved by all of the interference and diffraction stuff that we talked about last chapter. De Broglie then took it even one step further. Yeah, it looks like De Broglie, but it's De Broglie. He was, I don't know, Dutch, some weird European thing that don't pronounce anything. But he said that if light is acting like a particle, then maybe some things that we think of as particles are actually waves also. And so that means that anything could have a wavelength. He said, okay, if we know that the momentum is h over wavelength, we can say that that equals mv, and we can say that everything has a wavelength. And this turns out to be absolutely true. You have a wavelength. And you can figure out what it is by taking h over mv. Now, h is a really, really tiny number. And so to get a wavelength that you can see, you have to have a really, really, really small mass. So it's really only really small things that you can see it in. Your wavelength is tiny, 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 tiny. Can't see it, but you do have one. Generally, it's things that are smaller, like electrons or maybe some subatomic particles that you can actually see their wavelength and that they act like a wave, all the diffraction stuff that we did with light. Now, people that proved this is one of those things where they proved it accidentally. Two people, Davidson and Germer, basically had some research where they were studying the effects, they're testing nickel. They had some nickel that was sitting around, and somebody accidentally spilled some acid, or I don't remember exactly what they spilled on it, but they spilled it on it, it etched away at the nickel a little bit, and it left little bumps on it. And when they shot electrons at it to test its properties, they ended up with exactly the same pattern that we get from diffraction grating. And so they knew that the electrons they were shooting at it were acting like particles, just like the particles of light that we talked about last chapter did. And so they proved, accidentally, and got really famous, that the de Broglie wavelength was true for electrons anyway. It's a quick formula on the total energy of a beam of light, essentially. It's just saying that it's the number of photons times hf, which is the energy of one photon. Just realize that you can take the number of photons and multiply that by the hf thing. And so sometimes they'll ask you to find how many particles are going by per second. And so that you can use the power, to find that, because it's energy per second equals number of photons per second times hf. They'll have maybe one or two problems on that on a test. And the other one, there's another formula. Notice that there's a lot of, experiment. There's a lot of experiments. This one, Michaels and Morley, is one, I think that's spelled right, I think it's supposed to have an E in it, sorry, that proved that the ether didn't exist. They essentially shot a laser and then put a mirror and bounced half, it was a half silvered mirror, so half the light went one way, half went the other way. Then they put regular mirrors on the end, it bounced back into a half mirror, so the two things came together, and they got an interference pattern on a screen. And what they said was that if we are going through the ether, and the ether is moving in this direction, we're moving through the ether, it's all going that way, it should make a difference. This side, and this side should be different. And so if we turn it, our pattern should change. And it turns out that no matter what they did, the pattern did not change. And they essentially proved that the ether did not exist. No ether. That light will travel without any medium. And I think we'll watch a video on that. So if you don't quite get that, we'll go over that a little more. Last experiment, Rutherford scattering. Kind of make sure you keep Compton and Rutherford separate. Rutherford, you probably got in chemistry. Rutherford basically shot a bunch of helium nucleuses at a big atom, gold in this case. Here's our alpha particles, another word for a helium nucleus, and we shot it at gold. And at that time, they didn't know there was a nucleus, and so they thought that the gold was mostly going to go straight through, and they weren't going to be able to see much scattering. And it turns out that they would scatter a bunch, and some of them even went back the way it came, which is just crazy. And that's how they knew that there had to be a really, really positively charged thing right in the center of an atom that would make it, if it was coming straight in, it would bounce straight back out. There's no other way for that to happen, and it proved there was a nucleus. Rutherford, good guy, got rid of the plum pudding model. That was a weird one. Quantum physics. That's a little strange. The nice thing is the math's pretty easy. It's a good chapter for us.
Check out the lyrics.
We'll take it out with the lyrics.
Darkness. No parents. Continue darkness.
Continue darkness.